What is chemistry? It's more than just a jumble of elements, electrons, test tubes, and experiments that explode. Chemistry studies the stuff around us and how it changes. For example, it tells you what your body is made of, how antifreeze keeps your radiator from cracking in the winter, and why iron works.
Chemistry is everywhere. We study chemical reactions in biology, geology, engineering, and physics.
Warning! What you are about to see and hear may seem very strange. It may cause your eyes to cross and your toes to curl and uncurl convulsively. You may feel compelled to pull out your hair or use the bathroom. Should you experience these effects, don't panic.
As a mutual quantum number, titration, ZIMS, antibody, gimbal, electron, stoichiometry, mole fraction, beryllium, bobinia, lithiation.
Remember this. Chemistry looks and sounds strange because chemists have developed their own special language which they use to describe things. So, learn the language. Study the terms. Once you get used to the way chemistry sounds, you won't feel like it's causing a nuclear meltdown in your head. In no time, it will all make perfect sense.
Alas, no more delay. Let's get right to the heart of the matter.
Section A, Introduction to Matter.
Chemists study the interactions between energy and matter. Matter is anything that takes up space and has mass. When you think matter, think space and mass.
Matter can take up a little space with a lot of mass, like a rock, or it can take up a lot of space with very little mass, like air. Energy is not matter because it doesn't take up space or have mass.
Beware! We will use the terms mass and weight interchangeably. You can't do this all the time. For instance, mass and weight are totally different measurements in physics. But for our purposes, they're the same doggone thing. So, don't let it confuse you.
Energy does things to matter. For instance, as the fire burns the clothing on Bobo's butt, Bobo can see the light and feel the heat from the fire emanating from his hindparts. Light and heat are examples of energy.
Hey, how you doing? All right. Look, here's the lowdown on matter. It comes in 3 states: Massachusetts, Rhode Island, and Vermont. Hey, I'm just kidding, right? The 3 states are solid, liquid, and gas. When matter moves from one state to another, like when water evaporates or when ice melts, hey, we call that a change of state. Each solid, liquid, or gas has a unique set of characteristics, or properties, that we can observe and measure. Now, there are 2 kinds of properties. There's physical, and then there's chemical. Now, the physical properties, they describe physical attributes, right? Or physical changes. Temperature, height, weight, consistency, odor, and hardness, hey, they're all physical properties. They're the properties we can measure without changing the identity of the matter. For instance, melting point. It's a physical property, right? As ice turns to water, it's changing its physical state from a solid to a liquid. Hey, now water doesn't look like ice, but its basic identity is the same, right? Right. So, when we measure the melting point of ice, we're measuring a physical property. Boiling point, freezing point, and evaporation, they're all physical properties.
When we talk about the chemical properties of matter, we're referring to the way the matter acts during chemical reactions. For instance, water's ability to decompose into the elements hydrogen and oxygen is one of water's chemical properties.
Now, let me interrupt you here for a second. The wife and I are looking to buy a new home, and we'd like to buy some property, obviously, to put that home on. Now, you know, how much would buying some chemical property set me back?
Well, you gotta pay $1,500 down.
For what?
For the broker.
So not for the chemical property?
No, for the broker.
Ah. Huh.
Once water decomposes, it's not water anymore.
Well, what is it?
It's hydrogen and oxygen. Didn't you hear before?
Oh, yeah, you said that.
Right.
I forgot. I was thinking about, you know, buying a house.
You can't measure chemical properties without changing the matter. When iron rusts, the rusting process is a measurable chemical property, but it definitely changes the iron. You can only find chemical properties through experimentation.
Right.
This is why experiments are so frequent and important a part of chemistry.
Yeah. So here's a good way to think about the difference between physical and chemical properties. If you change the property and the matter only looks different, its identity hasn't changed, right? You're dealing with a physical property. Now, if you change the property and the matter's identity has changed, like when water breaks down into the elements hydrogen and oxygen, hey, then you're dealing with a chemical property.
Two types of matter are homogeneous matter and heterogeneous matter. Homogeneous matter has the same physical and chemical properties throughout it. In other words, all the stuff that makes up homogeneous matter acts pretty much the same way. Homogeneous matter is called a substance.
Distilled water, which has had all the impurities removed from it, is a pure substance and an example of homogeneous matter.
Heterogeneous matter is a mixture of substances. This rock is an example of heterogeneous matter since it was formed from fragments of other rocks. This limestone is also heterogeneous matter since it was formed from the secretions of organisms.
Ew, gross!
A mixture of substances is considered homogeneous if the mixture has the same physical and chemical properties throughout it. A homogeneous mixture is also called a solution.
On the other hand, a heterogeneous mixture has different chemical and physical properties, and these properties remain separate from each other. Orange juice is a heterogeneous mixture. You can strain the bits of orange out of the water.
You can separate both homogeneous and heterogeneous mixtures into their component parts by physical means such as distillation and the filtration we just did. Distillation is the process where we evaporate liquids or solids with heat, then condense the vapor back into a liquid.
On the other hand, you can only separate pure substances by chemical means, like adding heat or an electrical current. When you separate a pure substance, you get either an element or a compound.
So, you can see physical properties without changing the identity of the matter, but to see chemical properties, you have to change the identity of the matter. Can you say homogeneous? Homogeneous matter is also called a substance, and it has the same chemical and physical properties throughout. Homogeneous mixtures of substances, also called solutions, have the same chemical and physical properties throughout as well. Heterogeneous matter is a mixture of pure substances with different chemical and physical properties. You can separate heterogeneous and homogeneous mixtures into their components by physical means, but pure substances can only be separated into their components by chemical means.
Section B, the elements.
Elements are the building blocks that by themselves or with other elements make up all matter. An element is a substance that contains only one kind of atom. Right now, there are 110 known elements, and each element has its own unique atom that makes it different from the other elements.
So there you are. Close the door quickly. I must show you something very important. A tool that's essential for conquering widespread chemistry ignorance. The periodic table of elements. There are 110 different elements known to man, and you'll find them listed here. The elements fall into three categories: nonmetals, metals, and metalloids. The metals are on the left side and in the middle of the table, with the exception of hydrogen, which is on the left side but is not a metal. The nonmetals are on the right, and the metalloids are in a narrow diagonal strip between the metals and the nonmetals. Neon, argon, krypton, xenon, radon, and helium are called noble gases. That's because we do not combine easily with other elements to form compounds. In fact, neon, argon, and I are never reacted with another element, so they call us inert. I'm so ashamed.
Compounds are made of combinations of elements. A compound is a substance with two or more kinds of atoms combined in fixed proportions.
Dude, so water's a good example of a compound because it forms from the elements hydrogen and oxygen, right?
That's right, and a single unit of a compound is called a molecule. In the case of water, 2 hydrogen atoms and one oxygen atom combine through a chemical reaction and form a water molecule. In order for oxygen and hydrogen to come together to form water molecules, a chemical reaction has to make the atoms move from their original combinations to form new combinations. An increase in temperature can increase the rate of a chemical reaction. It's important to remember that during the chemical reaction, the atoms themselves don't change. There aren't suddenly any more or fewer atoms. They simply rearrange themselves to form the new compound.
The molecular formula of a molecule shows the exact number of atoms of each element that makes up a molecule. For water, the molecular formula is H2O. H2 means that there are 2 hydrogen atoms, and O, without any subscripts, means there is only 1 oxygen atom.
So you and everything around you are made up of elements.
A substance consisting of 2 or more elements combined in fixed proportions is a compound.
And the single unit of a compound, a chemical combination of 2 or more atoms, is a molecule.
Part 2. Units of measure.
Like physics and all the sciences, chemistry uses the metric system. You're probably used to the English system, but metric is even simpler since converting from larger to smaller units, or vice versa, is just a matter of prefixes. We all know that you know the metric system, but here's a quick refresher just in case.
Section A, the metric system and SI units.
This chart shows most of the commonly used prefixes. You'll see these everywhere, so it's useful to familiarize yourself with them now, particularly nano through mega.
Nano.
Oh, Mork, mega cool.
The International System of Units, also known as SI units, is based on the metric system and has been adopted by most countries. SI units are used for measurements and calculations in chemistry.
These are commonly used SI-based units, and you're going to get to know them all. Meters, symbolized by a lowercase m, measure length. Kilograms, abbreviated to kg, measure mass. Seconds, or a lowercase s, measure time. We measure volume in liters, symbolized by a capital L, and we measure heat in joules, symbolized by a capital J. Kelvins, symbolized by a capital K, measure temperature. Note that we don't say degrees Kelvin. This temperature measurement doesn't involve degrees, so just say kelvins. We measure large quantities of substances with a special unit called the mole, abbreviated MOL. Kelvins and moles are 2 important units of measurement, which we'll use constantly.
If you fail to take the proper precautions, these chemistry terms can hurt you. Be prepared. Put out the fires before they start. Learn the metric system and the SI-based units.
Section B, uncertainty in measurement.
Okay. All right. When we measure a physical property and we assign it a numerical value to that measurement, the numerical value is always an approximation. See, the accuracy of your measurement depends on the accuracy of your measurement instrument. So no measurement instrument is absolutely reliable.
The terms precision and accuracy are sticky. You may think they mean the same thing, but nope, not in science.
Precision measures the reproducibility of a result. In other words, if we take the same measurement 5 times, will we get the same answer all 5 times? If we do, our results are precise. Accuracy refers to how close our measurement is to the theoretical true value. When I say true value, I mean the value is determined by some brilliant chemist and listed in your textbook. If our measurement matches the theoretical true value, then the measurement is accurate.
When you decide how many digits you want to use to represent a value, you are deciding how many significant figures to use. Significant figures include the numbers on either side of the decimal point that seem reasonably certain. This is a little weird, but they're just some rules you need to learn.
For instance, the number 1.075 has 4 sig figs, and 2.00127 has 6 sig figs. The number 0.0075 has only 2 sig figs, since the zeros in the number only serve to locate the decimal point. Same with 0.0000362. Those zeros don't have value. They just tell you where the decimal point is. So, 0.0000362 only has 3 significant figures.
When you make calculations, you have to decide how many significant figures to use in your answer. If the answer has more figures than are significant, you can round it off. Here are some general rules for sig figs.
For addition and subtraction problems, give the result in as many decimal places as the number in the problem with the fewest decimal places. Remember, decimal places are only the numbers after the decimal point. For example, 10.712 plus 3.61 equals 14.322. But since the number 3.61 in the problem only has 2 decimal places, we can only use 2 decimal places in our answer. The final number just isn't significant.
Multiplication and division problems are handled a little differently. You round off the result so it has the same number of significant figures as the number in the problem with the fewest significant figures. Get the difference? With addition and subtraction, we rounded our answer off to match the number in the problem with the fewest decimal places after the decimal point. Multiplication and division answers are rounded off to match the number in the problem with the fewest significant figures, which can be on either side of the decimal point. For example, 2.32 times 77.96 equals 180.8672. But since 2.32 has only 3 significant figures, our answer can only have 3 significant figures. So we round the answer to 181. Got that? Good. Handle division problems the same way.
And since we're into reducing the numbers of numbers, let's not forget scientific notation. Scientific notation cuts back on the decisions you have to make about significant figures because it reduces the number of zeros in big numbers. You may know scientific notation already, but here's a review.
Scientific notation is a way of writing really big or really small numbers. It uses powers of 10 to express a number. For example, instead of writing 32,100,000,000, you'd write 3.21 times 10 to the 10th power, or 3.21 times 10 billion. It will appear on your calculator as 3.21E10 or 3.2110. A small number like 84 billionths would be written down as 8.4 times 10 to the minus 8th. A calculator would show either 8.4e minus 8 or 8.4 minus 8. Section C, Dimensional Analysis.
Relax. Although it sounds very complex, dimensional analysis is only a fancy term used to describe the process of converting units.
Here's the deal. We measure dimensions in units like the meters, liters, seconds, and grams we talked about earlier. Chemistry uses lots of different units, and sometimes you need a particular unit to do a calculation. If the unit you need isn't the one you're given in the problem, you have to convert units. You can convert units with the unit factor method. To use the unit factor method, write out the units, kilograms, seconds, meters, or whatever, for every quantity you're using in your calculation. Then carry the units through the calculation, treating them as algebraic quantities. Sounds tricky? It's not. Watch Willie the Wild Worm.
Wild Willie wants to visit his girlfriend Lily, who lives in a compost heap 7.92 miles away. Willie can only wiggle along 1 centimeter at a time. How many centimeters will poor lovesick Willie have to wiggle to cover the 7.92 miles between him and his beloved? Well, we have a problem with this problem. Willie measures his travels in centimeters, but we've measured his travel in miles, so we have to convert to centimeters, Willie's unit of measurement.
Using the unit factor method, multiply the quantity you start with by the appropriate conversion factor until you get the unit you want. In this case, convert miles to feet, feet to inches, and inches to centimeters, since centimeters is the unit you need for your answer. 1 mile equals 5,280 feet, 1 foot equals 12 inches, and 1 inch equals 2.54 centimeters.
To find out how many centimeters Willie has to wiggle, we set the problem up this way. 7.92 miles times 5,280 feet over 1 mile times 12 inches, over 1 foot times 2.54 centimeters over 1 inch. The first conversion factor, the one converting miles to feet, looks like this: 5,280 feet over 1 mile. 5,280 feet is equal to 1 mile, so in our equation, multiplying by 5,280 feet over 1 mile is just like multiplying by 1. You know that multiplying anything by 1 doesn't change the value. All we're changing here is the units. So this is when we treat the units like algebraic quantities. Remember crossing stuff out in algebra problems? When we cancel out the miles, feet, and inches in the problem, then multiply it through, we get 1.27 times 10 to the 6th centimeters. It's like we multiplied 7.92 times 1 times 1 times 1, changing only the units, not the values. And hey, don't forget the sig figs. 7.92 only has 3 significant figures, so the numbers in the answer can only have 3 significant figures.
Hey, babe, fix me a sandwich, will ya?
Chemists study the interactions between energy and matter. Matter is anything that takes up space and has mass. When you think matter, think space and mass. Energy, like light and heat, does things to matter. Solids, liquids, and gases are all examples of matter. And each solid, liquid, or gas has a unique set of characteristics or properties that we can observe and measure. There are 2 types of properties: physical and chemical. Physical properties describe physical attributes or physical changes. The chemical properties of matter describe the way matter acts during chemical reactions. 2 types of matter are homogeneous matter and heterogeneous matter. Homogeneous matter has the same physical and chemical properties throughout. Homogeneous matter is also called a substance. Homogeneous mixtures of substances, also called solutions, have the same physical and chemical properties throughout as well. Heterogeneous matter is a mixture of pure substances with different physical and chemical properties. Elements are the building blocks that by themselves or with some other elements make up all matter. An element is a substance that contains only one kind of atom. A substance consisting of 2 or more elements combined in fixed proportions is a compound, and a single unit of a compound, a chemical combination of 2 or more atoms, is a molecule. Precision measures the reproducibility of a result, while accuracy refers to how close our measurement is to the theoretical true value. When you decide how many digits you want to use to represent a value, you are deciding how many significant figures to use. Significant figures includes the numbers on either side of the decimal point that seem reasonably certain. To determine the number of significant figures to keep during addition and subtraction, give the result in as many decimal places as the number in the problem with the fewest decimal places. For multiplication and division problems, round off the result so it has the same number of significant figures as the number in the problem with the fewest significant figures.
So, dimensional analysis is just a fancy way to say unit conversion. Use the unit factor method to convert units of measurement. The unit factor method gets you the unit you want by carrying and canceling units algebraically.
Part 3. Stoichiometry.
Stoichiometry deals with the quantities of stuff in chemical reactions. We use stoichiometry to answer the question, how much?